It's kind of weird to think about molecules making choices, right? But they do. In the heat of a chemical reaction, a molecule has to make a split-second decision that can change, well, everything. Today we're diving into one of these secret preferences, a tiny but super important twist. Let's get into it.
So our story kicks off with what looks like a super simple reaction. You take this molecule, it's called a cyclobutene, basically a little ring made of 4 carbons. You heat it up, and pop! The ring breaks open and becomes a straight chain. Seems straightforward, right? But of course, there's a catch.
And the whole secret, the whole mystery is in the twist. See, when that ring breaks, the little groups attached to it, let's call them its arms, they have to rotate. They have 2 choices, twist inward or twist outward. Now, you'd think it might be a 50-50 shot, but it's not. For decades, scientists have seen that these molecules overwhelmingly prefer one specific twist. And the big question has always been, why?
Okay, so to crack this case, looking at the atoms isn't enough. We've got to go deeper. We need to peek into the subatomic world and watch this invisible dance of electrons that's really pulling all the strings. So yeah, let's take a much closer look.
And this whole thing? It's got a name. And honestly, it's a great one. It perfectly describes what's going on.
It's called torquoselectivity. Yet torco like torque in a car engine. It's all about a preference for a certain rotational force. For our molecule, it's that choice. Does it twist its arms inward or outward when the ring pops? And believe it or not, that one tiny choice completely decides what you get at the end of the reaction.
Now you might be thinking, don't chemists already have rules for this stuff? And yeah, they do. They've had a rule book for these reactions for ages. But it turns out that rule book was missing some pretty crucial pages.
So, the classic rules, the Woodward-Hoffmann rules, were a huge deal, an absolute game changer. They could tell you, yes, this reaction can happen if you heat it up. But that's kind of like having a map that just shows you that a road exists between 2 cities. It doesn't tell you which exit to take. Modern chemistry needs more detail. We're not just asking if it happens anymore, we want to know how. Which specific twist is it going to pick? And what's pushing it to make that choice?
And to get those answers, scientists brought out the big guns, the supercomputer. You can think of it as this incredibly powerful digital microscope that lets us see the reaction unfold in ways we could never see with our own eyes.
So instead of just dumping chemicals in a beaker, they can simulate the entire thing, frame by frame. What you're looking at here is basically an energy map. Every chemical reaction, and I mean every one, has to climb over an energy hill to get going. It's the price of admission. So what they did was simulate both paths, the inward twist and the outward twist, to see which climb was easier for the molecule.
And wow, this chart just lays it all out, doesn't it? For this molecule, look at that difference. The inward path needs way more energy to make it over the hill compared to the outward path. At the molecular scale, that's a massive difference. It's like choosing between climbing a gentle slope or a sheer cliff face. So of course, the molecule is going to take the easy route, the outward path, pretty much every time. But here's the thing. This tells us what it prefers, but it still doesn't tell us why.
All right, so now we get to the fun part, the detective work. By digging through all that simulation data, scientists uncovered 2 major clues that finally solve this mystery.
Clue number 1, and this is the big one, is what we can call the electron push. It all comes down to how electrons are getting shuffled around inside the molecule right as that ring is about to break.
Okay, so these colorful blobs you see, they show where the electrons are hanging out in the molecule. Now, as that ring gets ready to snap, electrons from other parts of the molecule can sort of push into the bond that's about to break, giving it a little help. The key is, this push works way better in one direction than the other. I love this analogy. It's like greasing only one side of a rusty hinge. Obviously, it's going to swing way more easily in that one direction.
And hey, don't just take my word for it. The researchers themselves said it best. It all boils down to how the electron pairs on the molecule's arms line up with the carbon-carbon bond that's breaking. When that alignment is just right, boom, you've created a path of least resistance, and the molecule is just going to follow it every time. Okay, but what happens if that electron push is basically a tie? What if both the inward and outward paths get a similar boost? Well, that's when our second clue comes into play. And this one is much more physical. We're talking about atomic bumping.
Take a look at this model of the inward twist. See how those hydrogen atoms are all jammed up against each other? They're getting way too close for comfort. Atoms, they really don't like being crowded. This atomic bumping, or steric repulsion if you want the technical term, it creates tension. It adds an energy penalty, making that inward path even more of an uphill battle. The outward path, on the other hand, it avoids all that crowding, giving it yet another edge.
So there we have it. The case of the mysterious molecular twist is solved. But you might be wondering, okay, that's cool, but why does this tiny little twist matter in the real world? Well, it turns out the impact is huge, way bigger than you might think.
What's so incredible about this is that it all boils down to two beautifully simple rules you can actually predict with. Rule 1, follow the electron push. Rule 2, avoid atomic bumping. That's it. And having that kind of predictive power is, frankly, the holy grail for chemists. It means you can design better drugs because you can control the exact 3D shape of a molecule. It means you can figure out way more efficient ways to make complicated chemicals. It opens the door to brand new materials, new technologies, all because we now understand which way a tiny molecule wants to twist.
So the next time you think about chemistry, I hope you remember it's not just random stuff bumping into each other in a flask. No, it's this incredibly intricate world of choices and hidden preferences. And when we understand those choices on the tiniest scale, it gives us the power to design our world on the largest scale. Which really leaves us with a mind-blowing question, right? If we can now predict, with confidence, the choice a single molecule is going to make, what's next? What kind of reactions will we be able to design and even control in the future?